remember them that when they show up in an equation, okay, by themselves, that they have to show up with another atom. So when we look at hydrogen gas being produced, it is H2. Okay? Is that going to become important? Yes. It's going to become really important when we move into the next concept. When we run a reaction, can we create or destroy matter? No. If we remember all the way back to our very first unit, we can't do that. So if a hydrogen shows up on the left-hand side of the equation, what has to show up on the right-hand side of the equation? Hydrogen. What if two hydrogens show up on the left hand? Two hydrogens on the right. I can change their locations, what they're attached to, but they must equal each other on both sides of the equation. Okay? Otherwise, I'm not looking at a proper equation. Well, does a proper equation matter? I don't know. How do you build a bicycle? Generically, how do you build a bicycle?
Tools.
Okay. We need a frame and we need wheels. So I just take one wheel and I attach it to the frame and I've got a bicycle, right? I've got a unicycle, not a bicycle. I need two wheels to make one bicycle. So the number of the parts are really critical to understanding the unit that you're making. Okay. If we built a car, how many wheels do we need?
5.
4. Okay. We need the proper number. If we have anything more or less, we aren't building a car. We aren't building a bicycle. Same thing's going to happen with chemistry. We aren't building the molecule that we're trying to design. Okay? So let's go through and look at balancing an equation. We must be the same on both sides of the equation. Okay? And by the same, we mean the same number of that atom. So let's come up with a notation that would allow us to do this as efficiently as possible. Okay? What we'll do is start with, I don't know, the first element I see. The first element I see is Na. How many sodiums are on the left-hand side of the equation? How do you know it's only one? I like your sort of sarcastic comments. We look at the left-hand side that I've underlined, and we look for the letter N and the letter A, and we count how many times those two show up in sequence. And we see it only show up once. So we would say 1. That was super creative. Okay? That is what you will do every single time. So let's move to the right-hand side of the equation. How many times does it show up over there? Once. Is our sodium balanced? Yeah, it's the same on both sides, so it's balanced. Okay? So we could now move to the next element. What's the next element that I see? Bless you. Wow. We've got hydrogen. Do we have to balance the hydrogen before we balance carbon or oxygen? No. It's completely irrelevant. Doesn't matter when we balance it, we just have to balance it. So how many hydrogens show up on the left-hand side of the equation? So we go through and look at the left-hand side of the equation, and I see a hydrogen show up once, I see a hydrogen show up twice, and I see a hydrogen show up 3 times. So don't I have 3 hydrogens? Why do I have...
6. Just kidding, 5.
Why do I have 5? No, I understand where you went with that.
Well, I saw the H2 on the other side.
Okay, so that's a different issue. That's on our product side, so we don't want to look at that one yet. We want to look at the left-hand side. I still only see 3 H's. Why is it not 3? We have to look at the subscript. The subscript immediately after now says that there are 3 hydrogens in that rightmost hydrogen box. So when I go through to total, what I'm actually totaling is 1 hydrogen here, 1 here, and 3 there. 1 plus 1 plus 3. Thank you. We get 5. How about on the right-hand side of the equation? We still get 5, so it's balanced. Next element. Okay, carbon. How many carbons do we have on the left-hand side of the equation? 2. Again, the subscript applies backwards. Okay? For those of you wondering about why I'm going through and really carefully labeling the subscript, even though we've got this kind of chorus of people telling me the answer, several people got this wrong on the test. Okay? It is easy to lose track of where the numbers are referencing. Be very careful with your analysis. There are 2 carbons on the left-hand side. On the right-hand side, we have 2. How many oxygens?
2.
And 2. Every element is balanced. What does that mean about the equation? The equation is balanced. So now we can use this equation potentially in other problems. Okay? But we have to make sure that we have it balanced before we can actually do any use with it. Okay? This coefficient, okay, applies to everything that comes afterwards. Okay? So we looked at our subscripts applied to only what's directly in front. Okay? We actually had coefficients through this whole equation. What was the coefficient for every single one of these? 1. The number in front is the coefficient. The number in front applies to what? Everything after it up to a mathematical symbol. Okay? So for instance, I wrote 3H2O. What does that mean?
3 H2s and 3 O's.
There are 3 H2s and 3 O's. What if I asked for how many hydrogens? There's 6 hydrogens. The 3 applies backwards, the 2 applies forwards. There's a total of 6 hydrogens. Why does the 2 not apply to the oxygen?
It's a subscript of the H.
The 2 is not immediately to the right of the oxygen. The 2 only applies to what's in front of it. Okay? So it's holding on to that meaning of counting the atoms, how many atoms are in that individual formula, how many of those molecules are in that individual equation. Okay? Questions about any of that? Okay, so let's bust out some rules. You guys always seem to balk at the Lewis structure rules, so I'm sure you'll love these. Balancing equations. Okay, remember the Lewis structure rules where I said you need to follow these rules so that you get the answer right? And you didn't follow the rules and you got the answer wrong?
Allegedly.
Allegedly. Same deal. Balancing equations. Follow the rules. If you do not follow these rules, you increase the odds you will get the question wrong. Okay, so be very careful and approach them. We followed each of these rules, or most of them, in that previous question. Predict the products. You notice I say if necessary. Okay, did we have to predict the products in the equation that we just balanced? No. Why not?
Because the answer was given.
I already told you what the products were. You don't have to predict them. You were told what they were. There's no predicting. Okay? Are you expected to be able to predict what the products are? Yes. For some equations, you are expected to be able to predict what the product is. Okay? We aren't there yet, so don't stress. Number 2, balance your formulas. Okay? Every single species in your equation is a formula. You need to make sure that formula is correct. What if that formula is not correct and you try and balance the equation? It's going to be wrong because you aren't starting from the correct position. So before you start balancing the equation, make sure your formula is correct. Okay? How do we know it's correct?
Neutral charge.
Our molecule must be a neutral charge. How do we know it's neutral charge? We know the charges on each of the ions going into that compound. How do we know those charges? We did a really good job learning all of those rules when it came to nomenclature from Chapter 6. Did you not do a really good job on Chapter 6? This is going to turn into a mess, to put it politely. Okay? So you need to know those charges to be able to apply to balance your formulas. Once your formulas are balanced, then you can balance the equation. It does not matter what element you start with. So you can start with any atom. Okay? You'll notice that I do have in parentheses other than hydrogen and oxygen. Why other than hydrogen and oxygen? How many different molecules have hydrogen? A lot. How many different molecules have oxygen? A lot. To balance hydrogen and oxygen, you'll have to be counting them in multiple locations on each side of the equation. That math can get really messy. So what we would hopefully do is balance the element that only shows up once on each side of the equation. That'll be easier to balance than in balancing the hydrogen and the oxygen first. Okay? If we balance those, that might self-balance the hydrogen and oxygen that we don't have to worry about it. Okay? For those of you that have to move it into further gen chems, up to 152, we add even more rules that have to deal with balancing hydrogen and oxygen that really suck. So don't worry about those rules yet. Okay? To go through and balance, you will place whole numbers in front of formulas. What's an example of a whole number? 1. How about another one? 3, 2, 5, 20. Okay. What's an example of not a whole number?
Square root of 2.
Square root of 2. Fractional values. Anything that gives you some decimal value, don't use that to balance an equation. That's a bad idea. Okay. The next part is that you will go through and you will repeat steps 3 and 4. You'll move to another atom and check. Reactant and product. Okay? If it doesn't balance, change the coefficients, the whole numbers in front, okay, to get it to balance. Here's the part that nobody likes to do. Step 6. You will check your work by repeating steps 3 through 5. Okay? Officially, that next step should probably not be 7, but should probably be about 10 or 11. What are these now invisible steps 11, 8, 9, 10? Repeating step 6. Okay. Anytime you change a coefficient, you must repeat your balancing process. Anytime. If you continue to go through and check and you keep changing numbers, what does that mean? You're doing it wrong. The question now becomes is why are you doing it wrong? Probably because you did not do step 2. Okay? Go back and check your formulas and make sure the formulas are balanced.
If they aren't balanced?
If they are not balanced, then you will have to make them balanced. Exactly right. Okay? So, we got a couple examples here. I'll go through and do one with you or for you, one depending on your perspective. Which one do you want me to do? Number 1. Okay, I agree.
No, the other one.
Number 2? Okay, number 2. There it is. We're going to do number 2. That's what you get for waiting too long. So, hydrogen. How many hydrogens on the left-hand side of the equation? 2. On the right-hand side? 1. That is not balanced. 2 does not equal 1. It needs to be equal to 2. So what do I have to do? I will put a 2 in front of the hydrogen on the right-hand side of the equation. Okay? That 1 will now become a 2. Why did I not change this to be H2Br?
Because the coefficient goes in front of it.
When we're balancing our equations, there's a couple big answers. Number 1, balancing an equation, we only change the coefficient. You cannot change the formula. Why can you not change the formula? Because then you're not doing the reaction that you were designed to do. Okay? You have to be sticking to those formulas. If the formula is incorrect, then you must fix the formula. So, next one. Bromine. How many bromines on the left? 2. How many bromines on the right? 2. Are our bromines balanced? Yes. What do we do now? Check your work. So we start again. I'm going to start with bromine this time just because I want to be wild and crazy. How many bromines on the left?
2.
On the right? How many hydrogens on the left? How many hydrogens on the right? 2. What do I do now? Check the work. Start with hydrogen. How many hydrogens on the right?
2.
Hydrogens on the left? How many bromines on the left?
2.
How many bromines on the right?
2.
What do we do now?
2.
Good answer. Check your work. Okay. You should be checking your work so frequently that you actually get angry that I asked you to check your work that much. Okay. If you aren't angry yet, check your work again. That's how often you need to check your work. There is no excuse for getting a balancing equation wrong because all you have to do is check it. If it doesn't match, you're wrong. Okay? You know you are wrong. You should be able to leave this next text being, I aced every single question, or I know I missed question 3, 5, and 6. And maybe 24. That one was just weird. Okay? So, your turn. We'll erase that middle one. You can now go through and balance all the others. If you got questions, raise your hand. I'll come to you. And then I said we're going to start again. Just checking. For the first one, what do we have? What element do we want to start with? Hydrogen. How many hydrogens on the left-hand side of the equation? 2. How many hydrogens on the right-hand side of the equation? 2. What do we do now? Go to oxygen. How many oxygens on the right-hand side of the equation?
Ooh, nice one.
Yeah. Stealthy. How many oxygens on the left-hand side of the equation? Is that balanced? No. What do we have to do? I need to bring in a 2 as a coefficient to increase the number of oxygens. Remember that 2 applies to everything afterwards, okay, including that oxygen. So there are now 2 oxygens on the right-hand side of the equation. Okay? And what you need to resist the urge from doing is saying, well, now it's balanced, I can move on. No, you need to go back and check. As soon as you change any coefficient, you must go back and check your work. Okay? Bar none, there is no exception to that. Okay? So we go back to our hydrogen and we say how many hydrogens on the left-hand side of the equation? 2. And on the right-hand side? 4. Is 2 equal to 4? No. So what has to happen? I need a 2 in front of the H2, which now means I have 4 hydrogens on the left-hand side of the equation and 4 hydrogens on the right-hand side of the equation. So now what do?
Check your work.
I go to oxygen. How many oxygens on the left? How many oxygens on the right? 2. Now what do? Check your work. We go back. Hydrogen. 4 and 4. Oxygen. 2 and 2. Now what do?
Check your work.
Okay. I'm getting a stare down, so I think we've already reached someone's anger level. Okay. Which then means we can stop checking. It's now balanced. Okay. And we can move on to the next question.
It's the smile we have that's like we have. You can see it on your face.
So, where do we start? How many aluminums on the left?
2.
On the right?
1.
Is it balanced?
No.
What do? Wow. Okay, I need to take a pause here. You guys got this?
No? Let's keep going with this.
Do this one.
Yeah.
Do this one.
Because I didn't get this one.
Okay, let's finish this one out, but it sounds like we're doing okay with balancing. It is going to keep coming back. You are going to have to keep working on it. Okay? Keep following those rules. It sounds like you guys got this down pretty well, so I'm actually kind of excited about this.
When you place a big number there, like with the 2, I know on a normal compound it carries through the entire compound, but with the parentheses,
It still carries through.
Okay, just check.
Doesn't change. Okay. What should we balance now? Oops, sorry. We need to make that a 2, right? There we go. Okay. Now what should we balance?
4.
So I've heard 2 interesting statements come out of that. I heard S being the next element there, not a bad idea. And I also heard SO4. Is SO4 an element?
No.
No. So how can we balance SO4? You can. Why can we balance SO4 as a unit instead of...
It's in parentheses.
Because it doesn't separate.
It's not even that it's in a unit, because we could start with SO4 as a unit, but in the reaction, it disappears. In this case, what we can do is look to both sides of the equation. I see SO4 here, and I look to the product. What do I have? SO4. Did the SO4 change in the course of the reaction? No. So I can create that as its own element.
I'm not happy. Fuck you, Dustin.
Let's go. calm down.
20 minutes.
How many sulfates do we have on the left? We have 3 sulfates on the left. So I heard a 1. Why 1? You're seeing the coefficient and applying the coefficient through, but you also have to remember you have the subscript. That 3 applies to whatever's directly in front of it. Man, you guys are punchy today. What is up?
He's the one that asked you for help. He's over here ridiculing me.
You guys are like, there's like 15 dollars. Who's the matrix?
Okay.
I would be yelling at you right now.
Let's calm down, guys. It's okay. The 3 applies to whatever's directly in front of it. What's directly in front of it? The parentheses. What is within those parentheses? SO4. So we have 3 sulfates on the left. Shift to the right, how many SO4s do we have? 1. Is that balanced? What do you need to do? We need to have 3. We will do that by putting a 3 in front there. We good?
No.
Was that recorded?
Hi, Mom, I'm on YouTube.
I'm hoping no. Hoping the microphone's not that good. People are just wondering why there's this weird shouting. What should we move to now? We can move to our barium, the next element. How many bariums on the left?
1.
How many bariums on the right? 3. Why'd you not say 2? Isn't barium in front of the 2? It's what's directly in front. What's directly in front are the parentheses, okay, which means that 2 only applies to that parenthetical, not to the barium. How do we fix our balancing for our barium? I need a 3 in front on the left. Okay. So our barium is now balanced. Now what should we do? Check our nitrate. How many nitrates on the left?
6.
We have 6. The 2 applies to the parentheses, meaning I have 2 nitrates, but then I have 3 of that unit. So this will be 2 times 3, and I end up with 6 nitrates on the left. How many on the right? 6. The 3 applies forward, the 2 applies back, and I end up with 6. Are the nitrates balanced? Yes. Now what we would go through and do is check our work, and we're just going to accept that. We've already hit enough angry yelling. Let's try and minimize that. Okay. We are now balanced. We can go back and check, and everything will balance out correctly, and we have our answer. Okay. Questions about that shorthand for that approach?
So if they're like that, we can put them together, so like SO4. So long as so like what if on this side, let's just say it was SO5?
Well,
Not work.
it would not work, and we'll see that actually in the next example. I think we see it in the next example.
So that's
I
when you have
erased
to
it. I
break
don't
them
remember.
up individually.
You'll have to balance them individually. Then.
Okay.
Exactly
now,
right.
what if the SO4 was in parentheses over here and this one wasn't? Would it matter?
One side is in parentheses. The other side isn't.
But I'm saying, what if that side had parentheses in it?
It doesn't matter.
It wouldn't matter.
It doesn't matter which side. As long as it's still SO4, you're fine. Okay. As long as it is still officially sulfate, is your answer. What's that?
If it's an ion.
We can't go with ion necessarily. Complex ion, if the complex ion stays the same, yes. But it must stay the same on both sides of the equation. Do you like balancing with complex ions? If not, that's fine. Go through and balance with the elements. You'll still be able to balance it. Okay? For those of you that tried to balance it with the elements, it turns into a mess really, really fast. Okay? It's a lot easier to balance with the complex ions. Okay? Other questions?
Say, anyone who's pre-calc, you can use the matrices for these, and it's like 10 times easier.
Would you like
Don't
to show
bring
me?
math into this, man.
I've actually heard that and I've never tried it. No, I don't. I don't know. So you could potentially, if you're in pre-algebra and want to apply your pre-algebra class, calc, your pre-calc class, pre-calc, your pre-calc class, you can solve using matrices. It does work as well. I think it requires too much abstraction away from this to deal with it. I have seen it, but I don't think it's worth the trouble. Okay. So now that we've got our equation all set up there, I actually want to introduce the potential for what we could ask as a question on the exam. Because that involved a whole bunch of, whoops, we need that 3 there. Whole bunch of extra work there, but some people could go through and look at this and be able to balance it without having to show any work. And to them, great, good job, you've balanced enough equations. Some of them are simple enough that you can do that, some of them are not. Okay? So asking it as a show your work question, pretty useless. Because I'm going to get some number of students that aren't going to show any work, and then I'm going to go, well, how do I grade that? Okay? Because you could have just as easily copied off someone else. So it will not be a show your work question. It will be straight multiple choice telling me some answers based off of the balanced equation. So what could I ask as a multiple choice question? Any guesses?
How many of whatever element is needed to balance the equation?
Okay, we could go with element, but it's actually going to be a little bit less complicated than breaking it down to the individual element. I'll say the coefficient in front of, this is how I could get kind of mean with it, in front of barium nitrate. Why does that become a little bit annoying?
Because you're not seeing the name, you see the symbol.
The name isn't in the formulas. You have to be able to do the name to the formula to figure out which one to look at. Though in this case, would it have mattered?
No.
Probably not, because hopefully you would have at least remembered that barium probably begins with B,
A, hopefully.
and the only 2 symbols that have B in them have what coefficient in front? 3. Okay. What numbers would I provide as multiple choice answers? 1, 2, 3, A, B, C, and now I run out of problems. I'd probably do D, 4, and because we have E, 5 choices, I'd probably say E, impossible.
Pine nuts.
Or pine nuts. Pine nuts shows up, I think, a couple times.
Is that the last exam?
Exactly. What does it mean? It doesn't mean anything. I just needed an answer choice to put in. That's it.
C bubbles. Start finding numbers.
Okay. So with those answer choices, we could go through and say 3C would be our answer. What if I had asked the coefficient in front of aluminum sulfate? Let's be a little bit nicer. Let's say it was this. Now the answer becomes 1. Right? Everybody got that? You're like, oh, that's simple. Why even throwing this in? Okay, so let's throw in the one last way that this gets presented, which tends to throw students for a loop. What is the sum of the coefficients? Let's throw down some answers here. Give me a second. I have to do some math. 4, 5, 8, 9. What is the sum of the coefficients? Which is the correct answer?
E. 9.
The answer is E, 9. So the common issue that students tend to miss is you go, well, 3 plus 2 plus 3 is not 9. What are you smoking, Mike? That does not add to 9. There's a 1 in front of the aluminum sulfate. You didn't include that in your addition. Okay? So watch out for that. What's the other fun part that we've already addressed with some of our other calculations? Where did 8 come from? Adding the 3, the 2, then the 3. Where did the 5 come from?
Only one side.
Just adding the products. Where did the 4 come from?
The other side.
Just adding the reactants. Where did the 6 come from? I don't know. 3 and 3. Okay. That's another impossible to tell or pine nuts. Okay? Questions? Okay. So we're going to clear all that, and now you'll jump in with a question. Yeah. Too bad. How about balancing the last one? So we'll go above this time. We can start with our hydrogen. How many hydrogens? 2 and 2. Okay. Well, last time we balanced complex ions. Is CO3 a complex ion?
Yes.
Yeah. So let's balance CO3. How many CO3 show up on the left? How many CO3 show up on the right? That's supposed to be a question mark. I can't balance the complex ion in this case because it was destroyed in the course of the reaction. What does that mean? You can't balance it as complex ions. You will have to balance it based on the elements. How many carbons on the left?
1.
Carbons on the right?
1.
Oxygens on the left?
3.
Oxygens on the right?
3.
I only see 2.
2 and then 1 over
There's
there.
1 in
Takes
each.
2 up.
Oh, thanks for helping me out.
Come on, I thought you were the teacher guy.
No, I'm just supposed to be here to make sure you can figure it out eventually. So you can tell me the correct answers. So what does that mean about our equation? It's correct. If I asked for the sum of the coefficients, one of the answer choices would be 0. Because you look at it, I don't see any numbers there, right? So shouldn't it be 0? You have to remember the implied 1 all the way through. The answer ends up being 3 for the sum of our coefficients. Make sense? Okay. 30 minutes. So, why are we balancing? This gets back into chapter 8. So if we look at our equation, it balances all the atoms. Okay? And our coefficients apply to the molecules or formula units. So that's kind of interesting. We have 2 uses of numbers, okay, where one applies to a molecule and another applies to atoms. Okay, well, which one is more useful? If I was to try and do this reaction, how many things am I mixing? How many reactants do I have? 2. I'm mixing aluminum sulfate with barium nitrate. Okay. If I go into the lab and I want to run this reaction, how many aluminum sulfates do I need to get a hold of? 1 of them. How many barium nitrates do I need to get a hold of? 3. And I put 1 and 3 together and I can get my products. And I end up getting 2 aluminum nitrates and 3 barium sulfates. Okay. What if I got 1 gram of aluminum sulfate? Switch that even differently, because I didn't mean to ask that question yet. Okay. How many of you have grabbed a single molecule of aluminum sulfate before?
Never.
How many of you have grabbed even just a single molecule of anything?
Never.
Right now.
Never. It is impossible for us to manipulate at the single molecule level, okay, at least in Gen Chem. Okay? After 10, 15 years of chemistry, maybe we'll be able to do that. You can then yell at your kids for having to be able to deal with that. Okay? You don't have to worry about that. When you go into the lab, you aren't grabbing a single molecule of aluminum sulfate. What are you grabbing? A whole bunch of them. Okay? Well, can you count each of them? No, why not? They're incredibly tiny. We can't see them. So we can't even count them to be able to do this process. Okay, well, so how do we even get them? How would I measure my aluminum sulfate? Come on, David, you said it earlier. Grams. We go in a lab, we go to the balance, we shovel some stuff onto the balance, we go, oh, I got 1 gram. If I take 1 gram of aluminum sulfate, how much barium nitrate do I need to add to it?
Same amount in grams.
3 grams?
Okay. So 3 grams, there's an interesting theory. Okay, so let's go back to building a bicycle. Right? So let's do the same general ideas we got up here. Okay, wheels. I ride an interesting bicycle. So there's my wheel. There's my frame. You can get a little seat there.
That's why I've never seen it.
Actually, not too bad. I've been doing this for way too long. Yeah.
It was a nice room.
Backwards.
More aerodynamic that way.
It's better down this.
Okay. So we now have effectively a chemical formula for building a bicycle, right? Did I hear a close?
Well, I mean, you messed up the wheel, man.
Let's assume our wheel's good enough. If I look at this formula, that frame is actually pretty solid. Would I actually be able to build a bicycle using this formula as shown?
No.
No. What's the issue with it? I'm missing a wheel. I need 2 wheels. Okay. We won't do a subscript because that means a molecule. We aren't saying wheels are a molecule. Okay, so we'll put a coefficient on that. Okay. So let's go back to the original question. What you guys postulated from the equation shown above, same context, right? That if I took 1 gram of aluminum sulfate, I needed 3 grams of barium nitrate, right? And then I could make those products. So what if I give you 2 grams of bicycle tires? How many bicycles can you make?
1 gram.
Okay, if I give you 2 grams of bicycle tires, how many grams of bicycles do you need, or frames do you need?
1 gram? Yeah, I don't know what you're trying to get me to get to.
How much does a bicycle tire weigh?
One bicycle tire.
A whole hell of a lot more than 2 grams.
Oh, hey, buddy, nice joke over there.
Okay? It's not a joke, it's getting you to think about the meaning of your formula. Let's take it a step further. If we used that logic and said 2 grams of these plus 1 gram of this, how many grams of bicycles would you have made?
1 tiny gram.
1 tiny gram. You took 3 grams and somehow made 1 gram? Wait, is that possible?
You get 3 grams of bicycle.
You get 3 grams of bicycle, but that doesn't correspond to the numbers that you've been manipulating here with the balanced equation. Does the balanced equation tell you anything about mass? No. What does it tell you about? How many of those particles are there? How many pieces you need? Your equation says nothing about mass. This should immediately be a bit of an issue, because when we look at the equation and I want to go into the lab and now run that experiment, I can't count the individual molecules like I can count the individual molecule or wheels and frames to make my bicycle. The only way I can measure out the molecules is to take mass. Okay? So now I run into an issue, because my experiment requires mass, my equation doesn't have units of mass. I need some way that I can get these 2 disparate pieces to overlap and make sense. Okay, well, maybe I could just come up with the mass of a single particle. What is the mass of a single molecule? How would we figure out that mass? Okay, periodic table. Fire away, how do you solve it? Okay, that's a good first step. We figured out that we need to look at the periodic table. Aluminum, I don't know why I didn't just trust your number, 26.98. But there's 2 of them, right? Okay, what's next?
Sulfur.
Sulfur, which is?
32.05.
Why do we break it down to sulfur and not SO4?
Doesn't have a mass.
SO4 isn't on the periodic table. Okay, so I have 32.07 for sulfur, but how many sulfurs are there?
30.
Oxygen times how many? 12. Why 12? 4 times 3. There's 4 within the parentheses. There's 3 of those sets of parentheses. So I've got 12 oxygens. We can add that all up. Anybody actually do it? No, I wish I had done it so I could actually write down a number, because everybody seems to like that. Okay, cool. 50, 100. Something bigger than 100. What?
85.05.
No.
Oh, wait, no, I didn't time it.
Today's a good day.
Wow. Spring break was last week, right, guys? Just checking.
My brain never came back with
I'm still recovering from exam.
342.17. Okay, 342.17. No.
No.
AMUs.
AMU.
So now you have to convert the AMUs to grams?
But now we have an issue. When we go into our balance room, what do we weigh? We don't weigh AMUs, we weigh grams. So I now know the mass of one molecule in AMUs, but AMUs is pretty useless in the lab. So what do I need? I need a conversion factor that allows me to convert AMUs. Oh, it is. Look at that. Convert AMUs into grams.
Was
So-
spring break like last weekend? Come on.
We would have to look up that conversion factor. And if we look up, literally, we've got 1.661 times 10 to the minus 24. Why did I put that in front of grams?
because AMUs, because
Grams are in one.
you want it in grams.
Because when we look at our conversion factor, where does the 1.661 times 10 to the minus 24 show up in front of? In front of grams. That's why it's written in front of grams. Okay? 1 AMU on the bottom. I can punch this into the calculator, and what do I get?
It's been a long week, what do you want?
Students
Dude, this week has been nuts. Yesterday in class, in organic class, we almost left and went to a dance party next door because they were blasting music. Yeah, it was really weird. So do we have a number here?
5.68337 times 10 to the negative 22nd.
should have wrote that in the corner.
Yeah.
Yeah. 5.68 times 10 to the minus 22 grams. Great. We now have a mass. I can now just measure that on my balance.
That's so small.
Okay. Your balance goes to what? 10 to the minus 3? Yeah. Yours is 10 to the minus 3. We're at 10 to the minus 22 for a single molecule.
That's because we're only in this chemistry, we're not like.
So let's move up to the next level chemistry, organic. We use fancier balances that cost an extra $1,000 per balance. And that gets us one more decimal. We're still missing, what, 18 decimal places?
Well, aren't you only like measuring like
Everything after.
4 molecules at this point?
Our issue comes down to a single molecule is so stupidly tiny that it does not make sense to measure them out as single molecules. It makes sense to scale this up to a different amount of molecules. I'm going to invent a unit that now takes that number of grams up to a reasonable value. So instead of measuring one molecule, I'm going to measure a lot more molecules. What's that a lot more molecule unit? Moles. Okay? 1 mole of atoms is 6.022 times 10 to the 23rd atoms. So this means when I go into the lab, I'm not going to measure out 1 atom. I'm going to measure out 6.022 times 10 to the 23rd atoms. What is that going to do for me as far as the mass? Okay, well, our number was 5.78, something like that. 5.786. 8 times 10 to the negative 22 grams per what? That was per 1 molecule of aluminum sulfate, right? What if I took a mole of those? Okay. So I want my units of molecules to cancel, so I'm going to do 6.022 times 10 to the 23rd molecules. I'm going to stop writing out molecules here in a little bit. What was it? Aluminum sulfate is 1 mole. So now instead of measuring out one molecule, I'm going to measure out a massive amount of molecules, but I'm going to call that a mole. Okay, I believe that was 345 point something something.
Yeah, the mole, it applies to all the atoms.
It applies to every atom within it, or it's a unit. So it's 1 mole of units is 6.022 times 10 to the 23rd units. So in this case, what's our unit? Aluminum sulfate. So it applies all the way through. Someone do the calculation for me?
342.
I knew it was a 2. Dang it.
342.
342 grams and 1 mole. Geez, was that number familiar to anybody?
No, not at all.
The AMU.
That was the exact number that we got when we totaled AMUs. Guess what the periodic table tells us as a unit? Both AMUs and grams. But it's telling us grams for a mole of those particles. So it's the mass for a very large number. What was the AMU? An arbitrary mass unit for 1 molecule. We picked this value of a mole of atoms to be this number because that then allows us to use the exact same number off the periodic table for our grams. That's why we use a mole. Mathematically, it comes out where I can use the exact same number and get the same conversion factor. It's lovely. It's such an impressive conversion factor that the guy that discovered this got to rubber stamp his name on top of it, and we call it Avogadro's number. Okay? And chemists everywhere love to talk about how great Avogadro's number is. You hear mole day and all this nonsense. Okay? This conversion factor rarely, if ever, gets used. Why? How often do you measure a molecule? The mass of a molecule? You don't. What do you measure? The mass of a lot of molecules. That lot of molecules happens to be darn close to that mole amount. So we can use the mole amount, and we use grams and moles because that's easier to work with than dealing with AMUs. Okay? That's ultimately its big design on where it's coming from, so it pretty much disappears once you get out of, oh my God, look at a mole, look at how cool it is. It is neat, it is. Neat number, but that's it. Okay? We then shift and stop talking about atoms, and we start talking about moles.
So would we, like, for instance, how would the test work? If you were to pose a
We'll look at conversion factors. Okay, so if we take a look at this, we've got Lego Minas Tirith from Star Wars. How many Lego bricks went into that?
Star Wars. I know my Star Wars.
It's also not Minas Tirith, which is Lord of the Rings. How many Lego bricks went into that? A lot. Do we really want to count each and every single one, or do we want to say maybe 1,000? Okay. You see the statement that we're making?
I got you.
We could go through and say that we had 2, 1 with a whole bunch of zeros after it. That's a lot of zeros to have to write. So instead, what could we call that? 2 million.
Yeah, like they made it.
We invented a new unit. What's that new unit? Million. What did we just do? That's not 20 million.
It has to be 20 million.
Yeah.
Oh, yeah, no, okay, never mind. I see what you're saying. Okay. We invented a new unit. That unit is called million. That allows us to simplify all these zeros. What did we do with a mole? Do you really want to draw out 23 zeros every time you do a calculation?
No, I'm good.
No. So we invent a new unit. What's that new unit? Mole.
Whoa.
Now I don't have to deal with all those zeros. That's the whole reason it's there. That's it. Okay? So, what we're now going to bring in with Chapter 8 is back to our metric conversions. And because you seem to have problems with metric conversions, we've jumped chapter 8 a little bit earlier so that you start working on these conversions before the exam. And then we'll double back to our equations and using the equations with conversion factors kind of all at the same time. So we get a little bit more practice with the conversions and the formatting of conversions, particularly with the new units of moles. Okay? So how do we set this question up? Our first step, what do we want? When do we want it? No. Micrograms. What did we start with?
Spring break is last week.
325 milligrams. Are milligrams the same thing as micrograms? No, so I need a conversion factor. Ideally, it would be milligrams and micrograms. Okay. Most people don't know that conversion factor. If you do, great for you. I don't, so stop making fun of me. But I can convert it to grams. Okay. Why did I pick grams? Because I think...
Oh, jeez. You're breaking my immersion.
It's been a great class.
I'm glad I'm going on vacation. What's our relationship between grams and milligrams? Our power of 10 always applies to our base unit. The base unit is grams. 10 to the negative 3 grams is 1 milligram. What would my units be? Grams. Okay, the milligram units cancel. Are grams the same thing as micrograms? No, so I need a new conversion. In that new conversion, I want to go from grams to micrograms. Okay, is this a conversion factor that I know?
Yeah.
Well, I flipped the front of the exam, and the front of the exam tells me that, yes, I do know this. It tells me that micro means, just curious, 10 to the negative 6?
Really small.
1, what's my unit? Micrograms. I punched it into my calculator, and I now have my answer. To do these conversions, we needed a conversion factor, a unit that related two things. Say like 1 mole is 6.022 times 10 to the 23rd. 1 mole of atoms is 6.022 times 10 to the 23rd atoms. Like that kind of conversion factor? Yeah, exactly like that kind of conversion factor. So you will now be using that conversion factor when you're going through and trying to calculate the number of atoms in a substance. Okay, so you need to remember that one. Okay. I will not give you 6.022 times 10 to the 23rd. You will need to memorize that. Why? If all the other chemists have fun with their stupid mole name day things, I'm going to make you memorize this.
So June 2nd?
What?
Get it like apple, the pi day is
Yeah.
3.14.
Yeah, that works.
June 2nd.
Oh.
Yeah.
No, because it's 6.02, so it's 02 June 2nd.
I got you.
Most jokes are done anyways.
One more way to relate this. A farmer has 72 chickens, and each chicken lays 2 eggs per day. How many eggs can the farmer collect per day?
Wait, a farmer has 72 chickens and each chicken lays 2 eggs a day. How many eggs does the farmer collect per day? 72 times 2.
144.
Yeah, that would.
So what do we do? Same thing we've always done. What do we want for an answer?
Eggs.
Not quite.
Collected.
Per day.
Eggs per day. What do we know to begin with? We have 72 chickens. Okay, that one's a bit odd to start with. Why is it odd to start with 72 chickens? Is chickens eggs or day?
No.
No. So that one's a little bit weird. It's not wrong, but it's a little bit odd to start with that because we don't know necessarily where to put it. Okay. What's the next thing we know? 2 eggs per chicken per 1 day. What happens to your units? Chickens cancel, and what do we end up with? 144 eggs per day. Okay. I always feel bad about this example because of this next part. Let's say the farmer has a hard time counting above 10.
Oh.
That's why it's a
Okay.
Nice one.
I get mauled by farmers. We've got 144 eggs per day. He's asked you to tell him how many eggs per day he's going to get. You come back and tell him 144. He's going to have a problem with that. He can't deal with 10. Numbers bigger than 10. Is 144 bigger than 10? Yeah, or sorry, bigger than 20. We need to do bigger than 20. Can't deal with bigger than 20. Why 20?
Because it's more than 10.
Fingers and toes. Okay. Can't deal with numbers bigger than 20. 144 is bigger than 20, so he cannot process this information that you are giving to him. Okay. How can you change the information so that now he can understand and process what you're telling him, but still learn about the amount of eggs he's getting? Scientific notation won't help because then you bring in exponents. And if he can't count higher than 20, he's not going to like exponents.
Do you do it eggs per hour?
Eggs per hour is only going to increase it.
Oh. Eggs per week?
He wants day, but not a bad idea. You go to the store and buy eggs. How many eggs do you buy? Okay. A couple people shouted out.
Does he know what a dozen is?
A dozen. I don't know. But he can't count higher, can't deal with numbers greater than 20. Can you explain to him what a dozen is?
Maybe.
12.
1 dozen is 12 eggs. Well, you can deal with 12 eggs. That's less than 20. How do you change your calculation so that he can better understand? I don't want to look at the number of eggs now, per se. I want to look at the dozens of eggs. What is the conversion factor between dozens of eggs and eggs? 1 dozen is 12 eggs. Now when we go through and look at our answer, what do we end up with? 12 dozen eggs per day. You explained to him what a dozen meant. It just meant 12. And he now has 12 sets of those 12. Cool with that. You've now explained to him something that he can't comprehend. How many of you can comprehend 10 to the third? Try that again. Let's try 10 to the 23rd.
A little hard.
How big is 10 to the 23rd?
Too small.
Okay. That is really, really big. You don't have enough fingers. That's not going to work. Okay. I don't know why doing the wave gives you more fingers. So what do we end up doing? We end up inventing a unit to help us better comprehend. What is that unit we invented? 1 mole is 6.022 times 10 to the 23rd eggs.
I really think you get the concept.
Okay. That's all a mole is. Nothing fancier than that. Just an extra conversion factor. That then means you have to use and reuse this again and again and again. Okay? If we take this back to our equation, I got tired of drawing them apparently.
Why did you have a bicycle for eggs?
What can we use for... Let's just... What is the mass of 1 mole of carbon atoms?
6.022 times 10 to the 23rd.
Okay, so that was kind of a bad question. I need to fix that. What should I fix it?
6 grams?
In grams. So for those of you shouting out 6.022 times 10 to the 23rd, great, you've got that number, but you did not memorize the units associated with it. Okay. The units associated with that number were the number of atoms in a mole, not grams.
Dang it. 12.01 grams?
Where are you getting that 12.01 from?
Yeah, that's the atomic mass of carbon.
Okay, you just said the atomic mass. Thank you for making that mistake.
Oh.
Okay. You're right. If it's atomic mass, it's 12.01 AMUs. I wanted grams. How do I convert AMUs to grams?
Use the conversion factor of AMU.
I need my AMU to gram conversion factor. What was it, 1 times 10 to the minus 24 grams was 1 AMU, right? Okay. Our AMU value here, that was the mass for one atom. So if we go through and do this calculation, what's the unit, or what's our answer? Grams per atom. I didn't ask for atom, I wanted moles. Okay, I need to get rid of atoms, and what do I want? Moles. Do I have a conversion factor that relates atoms and moles?
Yes.
What is that? 6.022 times 10 to the 23rd atoms is 1 mole. Okay. Since there is some question here, where did this number come from? Top of the screen, so it is given to you. The next number, where does that number come from?
You're supposed to know it.
Memorize.
You need to memorize that. Wow, I can't write. Good thing we're done. You punch that into the calculator, and what do you get? 12.01 grams per mole. What is the relationship between 1.66 times 10 to the minus 24 and Avogadro's number? They are inverses of each other. They allow you to use everything on the periodic table as grams per mole.
So on the test,